in our neighborhood, University of Illinois at Urbana-Champaign. His research interests are in network and distributed system security, and he's currently working on projects in secure messaging, dynamic coalitions, web services, and wireless sensor networks. Here's Dr. Khurana.
Thank you, Lingui. As Lingui said, I'm Himanshu Khurana from the National Center for Supercomputing Applications. I'll be talking today about an approach we are trying to propose for minimizing trust liabilities in secure messaging infrastructures. Please feel free to interrupt me anytime with clarification questions or comments. That's no problem at all. So, many large-scale collaborative applications need a messaging infrastructure that allows the collaborating entities to talk to each other or exchange messages without concern for message transmission and delivery. For example, groupware applications today typically assume the presence of an email infrastructure for group communication. Conferencing, such as video conferencing or audio conferencing, assume the presence of multicast group communication infrastructures. Tickers, such as stock tickers, news tickers, etc., assume the presence of a PubSub infrastructure and take advantage of it. However, for widespread deployment and use of these such applications, you need a secure messaging infrastructure. And by secure, we mean an infrastructure that provides support for integrity, authentication, confidentiality, and availability. Integrity and authentication is typically provided today by the use of digital signatures and together with certificate authorities and public infrastructure. So they work pretty good, but they impose large certificate distribution revocation problems. Confidentiality is hard to provide in messaging infrastructures, and wherever it is provided today is done by the use of trusted servers that do key management on behalf of the users. Consequently, the servers bear significant trust liabilities of maintaining the confidentialities of those messages and keys. For example, a group controller in a group communication system today can store all the long-term session keys, long-term as well as the session keys. Availability problems can be solved via replication, but with the caveat that if you replicate any server with keys, you can reduce the security of the system. The focus of our work is specifically on confidentiality. That is, how can we make messaging infrastructure support confidentiality but minimize the trust liability that is borne by the servers providing this security support? So why is this an important problem? So it's an important problem because servers are now being attacked on an increasing basis. Electronic crime is on the rise. For example, in the summer of 2004, there was a large-scale attack on the supercomputing infrastructure of this country. Many systems at NCSA were compromised at San Diego, and etc. The attackers there compromised remote users, used these user accounts to go to the servers, and did privilege escalation attacks to get root access on servers. And they did a combination of denial of service, some integrity modification, or they were planning maybe just using the systems to launch denial of service attacks elsewhere because they didn't have access to this great network infrastructure. And I'll go into this a little bit more detail, but they specifically tried to violate the confidentiality of email in the system, specifically the email of the security administrators. So we want to provide resources that minimize this trust liability so that even if the servers are compromised, you do not lose confidentiality of all data and communications in the system. This is not an easy problem to solve. If we say that the servers should not have the keys, that directly means that the server should not be able to access the messages that traverse the messaging infrastructure. However, it is these servers that must process these messages in order for delivery. For example, in publish-subscribe systems, the broker network does the matching and routing on the messages in order to deliver it to subscribers that have interest in those events. As I mentioned earlier, in group communication systems, the servers must process the key management messages in order to update the session keys whenever a member joins or leaves the group. Furthermore, the solution must scale to support a large number of users. This specifically means that you cannot have any key establishment between the end entities, which is clearly an order n-squared problem and leads to higher overhead. So our approach to address these challenges is to explore novel encryption techniques and then use these techniques to design messaging infrastructure. To study this problem, we have chosen three specific infrastructures, namely group communication, publish, subscribe, and email. At the end of the talk, we'll see what characteristics of these systems are related and what other systems could be there where this could be applied. The encryption techniques that we look at is namely proxy encryption techniques. This is an idea that came about in the late 90s, which allows a transformation agent to convert ciphertext from a ciphertext that is a message encrypted with one key into ciphertext for another key that is a message encrypted with another key without revealing the plain text or the secret keys to the transforming agent. So let's look at an example construction in El-Gamal. So in El-Gamal, let's say the keys for users A and B is as follow. SKA is user A's decryption key, while PKA is his encryption key. Similarly for user B. Let's say we have transformation agent T, to which we give a proxy key called pi, which is the difference of the decryption keys between users A and B. Now you encrypt the message for user M, user Alice A, as follows. This is the standard El-Gamal encryption of the message. And you want the transform agent to transform the message such that the outgoing message is encrypted for user Bob. What T would do is to take the message and simply encrypt it with a function of the proxy key. With simple mathematics, the private keys here cancel out and you get a message that's encrypted with user Bob's public key. Now here, the transformation agent only has access to the proxy key, not to any secret keys. So consequently, the trust liability in the transform agent is minimized because it no longer has the decryption keys, but can still enable the transformation. The applications that have been looked at earlier in this context are key escrow. For example, escrow with description escrow for the FBI or something, smart card key management, and file sharing, where one user wishes to delegate to a transformation agent the capability to assign decryption rights for files. To our knowledge, we are the first to look at extending these schemes and then analyze them in the context of large-scale collaborative applications. So in the next few slides, I'll take one messaging infrastructure at a time and show how these schemes need to be used and how this minimization is realized. So first is email list services. This is something we are all familiar with, as they typically clog a large percentage of our inbox on a daily basis. An email list service comprises a list moderator, which is a process or an entity that creates lists and subscribes users. Then there is a list server that creates lists, forwards emails to all valid list subscribers, and optionally archives the emails as well. And then there are users or subscribers that subscribe to lists with the help of the list moderator and send and receive emails with the help of the list server. The reason why these mailing lists or email list services are so popular is because the list server bears all the overhead of list management and forwarding the emails. The user has to do little or no work. They are increasingly popular for exchange of both public and private content. Whenever there's private content involved, security becomes an important concern. For example, there are currently over 300,000 lists registered on listserv, which is a common list server system, while only 20% of the some public content, meaning the large amount of content is private. However, that private content is not actually supported by any security techniques. They just say that you do not have access to it, but there is no cryptographic support for this privacy. So there is need to develop solutions that provide security in this environment. There has been a lot of work done for two-party email exchange security, but definitely not enough for mailing lists. To that end, we have developed a solution called CELS, Secure Email List Service, that provides solutions for confidentiality, integrity, and authentication. So why do we need these security properties, and what do they mean in this context? Confidentiality means that only authorized users, that is, the list subscriber, should be able to read the emails. In particular,